we're back on 3.4 to finish up two more examples of concavity and points of inflection and inflection points. Okay, so our example 3 is another polynomial function. However, it's given in factored form. I'm looking at f of x equals 3x times the quantity of x minus 2 cubed. We are going to notice the fact that this function itself is a nice polynomial function. There are no asymptotes, there's no holes. It's everywhere continuous, everywhere differentiable, even twice differentiable, so we're not going to have any problems with our second derivative. So we're going to go ahead and take our first derivative here. I have to use a product rule. I'm looking at the first times the derivative of the second, which would be 3 times x minus 2 quantity squared times 1, which is the derivative of the x minus 2, close, first times the derivative of the second, plus the second, which is x minus 2 quantity cubed, times the derivative of the first, which is just 3. And I'm going to just make this a little bit neater here. I'm going to take my 3 times 3 and bring 9x to the outside, multiplied by x minus 2 quantity squared. I'm going to bring my 3 to the outside, x minus 2 quantity cubed. And now I'm going to look for any greatest common factors because I would like to factor this first derivative before I move on any further. I'm looking at a 3 common, and I'm looking at a couple of x minus 2's common. So 3 quantity x minus 2 squared. If I were to factor out a 3 and an x minus 2 squared from this part of my derivative, I would be left with a 3x, copy my plus. And if I were to factor out a 3 times x minus 2 quantity squared from the other part, I would just be left with a singleton x minus 2. So let's make this a little neater before we take our next derivative. I'm looking at 3x minus 2 squared. 3x and x is 4x minus 2. And I can't help myself. I notice that there's a 2 common in this binomial. So I'm going to factor that 2 out of the binomial, toss that 2 over to the 3 and make it 6. Got my first derivative is now 6, open parentheses, x minus 2 squared. And when I factor the 2 out of here, I'm going to be left with 2x minus 1. And this is a nice format for this first derivative because now when I take my second derivative, I can just do a singleton product rule and not get messed up with anything else. So here we go. Here's my second derivative. This whole thing, 6x minus 2 quantity squared, that's going to be considered my first, times the derivative of the second is just 2, plus the second, 2x minus 1, times the derivative of the first. The 2 times 6 makes 12. Copy x minus 2 quantity to the first, and then chain rule of the derivative of what's inside my parentheses gives me a 1. Now I'm going to make this nice and neat again, I hope. 2 times 6 giving me 12, x minus 2 squared, and I have a 12 here, so plus 12, I have an x minus 2, and then a 2x minus 1. Alright, this is my second derivative, which I prefer to have in factored form, so that's exactly what I'm going to do is pull out any common factor that I can see. I can see a 12 common in both the terms, and a singleton x minus 2 is common to both terms. I'll factor out a 12 x minus 2. If I factor out a 12x minus 2 from the first set here, I'm going to be left with a singleton x minus 2. And if I factor out a 12 and an x minus 2 from this second part of my derivative, my second derivative, I'm just going to be left with that 2x plus 1. Oh, minus 1. There we go. So I have a second derivative with respect to x, 12 x minus 2, and if I simplify everything in here, I'm looking at a what? 3x minus 3? And yeah, you guessed it, I can't help myself. I'm going to pull a 3 out of here, multiply that 3 by the 12 and call it 36. 36 x minus 2 quantity x minus 1 for my second derivative. And this second derivative is a nice polynomial function. I can tell what's going to make it 0. That's going to be an x equals 2 and an x equals 1. So I'm just going to write here x equals 2 and x equals 1. Those are possible points of inflection. It's possible that if the second derivative is going to change sign from positive to negative or negative to positive, it would do it at these values, which would of course make the second derivative equal to 0. Alright, so I'm just going to write equals 0 right there. And that tells me that the 2 and the 1 were the values for x that made this second derivative equal to 0. Alright, so we are going to create a number line from negative infinity all the way to positive infinity. And I'm going to plot both those points on here. Here's a 1 and here's a 2. So I'm putting two numbers on my number line, but make sure you understand that actually gives us 3 different intervals. So here are my intervals. Negative infinity to 1, 1 to 2, and then from 2 to infinity. Are my intervals. Next thing I'm going to want are test points. I always like to put the value that split my interval up on these vertical lines. So give me a point in between a negative infinity and a positive 1. I'm going to pick negative 10. Something in between 1 and 2, I'm going to pick 1.5. And something between 2 and infinity, I'm going to pick a positive 10. And since I'm dealing with concavity now, I really want to test my second derivative for each of those test points. So let's do this. Let me see, my second derivative is in really nice factored form all the way down here. So I'm going to be playing with that concept right there when I do my test point. Take a negative 10 and put it into both of these factors. Negative 10 minus 2 makes negative 12. Negative 10 minus 1 makes negative 11. So the 36, of course, is positive. I'm just going to write a positive sign. I had a negative when I put my 10 in here. Negative 10 minus 2 gave me that negative 12. And then that negative 11. A positive times a negative times a negative. These negatives pair up to make a positive. So this overall answer is positive, which is greater than 0. That tells me that the original function f, up there, had to definitely be concave up because its second derivative is positive. Just for that interval. 1.5. Let's take the 1.5 and let's see here. The 36 is definitely positive already, so I'm going to put a plus sign in there. Take 1.5 and subtract 2. That's going to yield a negative result. And when you take 1.5 and subtract 1, that's going to yield a positive result. So negative result, positive result. A positive times a negative times a positive should be negative, which is less than 0, which tells me that the original function is going to be concave down on the interval between 1 and 2. Let's take our 10 and let's see what happens when we put a 10 in. Obviously the 36 stays positive, that's not affected. 10 minus 2 is a positive 8, 10 minus 1 is a positive 9. So this is positive, positive, everything's positive here. Multiply it all together, you still have positive, which brings me back to f being concave up once again. So the function f is going to be concave up on this interval and this interval, concave down on that interval. Are we going to have any points of inflection? It all depends on whether f itself changes concavity on a point that's defined in the original function. Is x equals 1 defined in the original function? Of course it is. The original function is a polynomial function. It's everywhere defined. That pretty much wraps up the argument for x equals 2 as well. We're changing concavity from concave down to concave up at x equals 2. So we should be pretty good at stating our 2 points of inflection, our 2 intervals of concave up, and our 1 interval of concave down. So let's go ahead and put our answer here. F is concave up on negative infinity, comma 1, and again on the interval between 2 and infinity. And I want to say, because we always have to give our reason why f is concave up. F is concave up because f double prime, which is my second derivative, is greater than 0. F is concave down on the interval in the middle between 1 and 2. And this is because, I suppose I can write that right here, f double prime is less than 0. And f has inflection points at 1 comma, I think I can put that here, 1 comma, now I need my y-coordinate for my inflection point. So I'm going to take the value of 1 and I'm going to go back to the original function where I get my height, and I'm going to put a 1 in here. 3 times 1 is just plain old 3. 1 minus 2 is negative 1, and when I cube negative 1, I get negative 1. Negative 1 times 3 is going to give me a negative 3 for my y-coordinate when x is a 1. And again, I'm going to have another inflection point when x is 2. And I'm going to cheat because I already know what it is here. I put a 2 in here. This 3 times 2 makes 6, but 2 minus 2 is nothing. And when you cube 0, you get 0. You times 0 by 6, you get 0. So the y-coordinate when x equals 2 is a 0. And that's why I already put 2 comma 0 there. I knew that answer. All right. So why do we have those inflection points? I need to say because why. Why is that true? F changes concavity. And that finishes the question. And the question was, state the intervals where the function is concave up, concave down, and state any inflection points. Give reasons for your answers. So here we have it. Nice polynomial function. It's a 4th degree polynomial function. Looks like a leading coefficient, so it's starting high, ending high. And we have some nice concavity. Everything's nice and smooth about this polynomial function. So I'm going to stop this example and I'm going to go ahead and give you a rational function example. Okay. Let's go ahead with f of x equals x squared plus 3 divided by x squared. Not quite as nice of a function as the polynomial function, but it's not too bad either. Just analyzing this rational function for a minute. This function is neither top-heavy nor bottom-heavy. The degree of the numerator is a 2. The degree of the denominator is a 2. That tells me I'm going to have a horizontal asymptote. And the horizontal asymptote will be the ratio of the leading coefficients from your numerator and denominator. So 1 over 1, simply y equals 1. I am going to have a vertical asymptote because there is an x value that makes the denominator equal to 0, but not the numerator equal to 0. So that value is, of course, 0. So this is x equals 0. X equals 0 is the y-axis. So I definitely have the y-axis as a vertical asymptote. All right. I need to make sure that I'm familiar with the fact that x is not going to be 0 for this problem. If I think, for some reason, that I'm going to have an inflection point at x equals 0, I will be mistaken, because you cannot have an inflection point at a value of x that is not defined in the original function. Make sure you know that. This is a point of discontinuity. It is a non-removable discontinuity because it is a vertical asymptote, as opposed to a hole, which would be a removable discontinuity. Okay, so we're going to go ahead and take our first derivative. A little piece of me wants to do this division and just make it a little easier, but I'm going to go ahead and use the quotient rule, just for practice for everybody. You're looking at the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared, or low to high minus high to low, all over low, low. So we're going to neaten this up a little bit, if that's a word. Gives me 2x cubed minus 2x cubed, and then minus 6x all over x to the 4th. This can say goodbye with that. Opposites attract because when they meet, they combust and it's all gone. The x and the x to the fourth can cancel, and I can just have negative 6 over x cubed. This is such a nice function. I would just like to call that negative 6x to the negative 3. Because when I do my second derivative, I don't need to do that quotient rule anymore. I can just go ahead and use the power rule. Okay, notice here that the first derivative is not defined when x equals 0, but that doesn't mean I have a critical number because when x is 0 I have a vertical asymptote. Anyhow, I have a point of discontinuity. So when I take my second derivative, I have negative 3 times negative 6, which is going to give me a positive 18, x to the negative 4. So that's 18 over x to the 4th. It doesn't look to me like there's any way I'm going to make this thing equal 0. Do you think there's any way 0 will equal 18 divided by x to the 4th? This is never. There's no x value that will ever make that happen. And we already know that the second derivative is undefined when x equals 0. Of course, it's not a point in my domain anyhow, not a value of my domain. So I guess I'm ready to find any intervals of concavity. I do know that I won't have any inflection points whatsoever, because I can't have an inflection point with x equals 0. That would make my second derivative undefined. Would be nice, but I can't have it if it's not in my domain. And there's no way to make the second derivative equal to 0. And from the theorem, I think it was 3.9, 3.8, we learned that if you are going to have an inflection point, you do have an inflection point, that at that inflection point, either the second derivative is equal to 0 or it's undefined. I don't have any of those. So I know I won't have any inflection points. But let's go ahead and build our intervals so we can determine concavity. We always draw a number line when we're building our intervals. The only point I have to plot on this whole number line, however, is x equals 0. So my intervals are pretty simple. Going from negative infinity to 0, and then I'm going again from 0 to positive infinity. I'm looking for test points. Test point between negative infinity is 0, and 0 is going to be my negative 10. Test point between 0 and positive infinity is going to be a positive 10. And then we're on our second derivative at the test points. Here's my second derivative. I have a positive numerator and I have a positive denominator. Regardless of my test points, when I raise anything to the 4th, whether it's positive or negative, not 0, but any non-zero number to the 4th, this answer is going to turn positive. So I'm looking at positive over positive, that's greater than 0, positive. Positive over positive, that's greater than 0, positive. This tells me that the function f itself is concave up, concave up. I don't even have any concave down. Should make good sense to you though. Alright, so what do we know? We know that, let me see if I can come over here and just do this a little bit. We know that f is concave up from negative infinity to 0, and again from 0 to infinity. Don't say all real numbers because you cannot include x equals 0. We can't say that a function is concave up over the asymptote. It's not happening. Why is this true? This is because f double prime is greater than 0. F is never concave down. Why is that true? Because f double prime is never less than 0. And f has no inflection points. Because f does not change concavity. And that looks like the end of our question. Everything is looking good. Looking good, looking good. All right, everybody should be finishing up 3.4, numbers 2 through 12 even, and we're going to even continue further than that for tomorrow after. All right.